In this screencast, we're introducing the spring and the forces that a spring applies to a body. And so our goal here is to find the equation of motion for this simple one spring system that's operating in straight line motion. And so to do that, we're going to follow the steps that we've established before. And we start out by drawing a reference frame. So reference frame I. And then we need a coordinate that defines the location of the mass. So we'll define this coordinate as x, and it's related to this origin within the reference frame O. Now to find the equation of motion, we're going to apply Newton's second law, which is F equals ma, and we need to determine what the forces are that are acting on this mass m. And the only force that we're showing here is a spring force. A spring exerts a force that's proportional to the distance that the spring is displaced from the resting length x naught. And this is governed by a coefficient k naught. And so the magnitude looks like this, where we have the spring force, which we'll call F sub s, is equal to, this is k x minus x naught. And so we've put these in absolute values just to say that we're only dealing with the magnitude, and we'll deal with the direction in just a moment. The units of our spring constant are in kilograms per second squared. Now this magnitude, F sub s, is not always going to remain constant, because if we take a look at our system model, and if we're pulling our mass to the right, then the spring force will be opposing that, and it's going to point to the left. Similarly, if we push our mass to the left, then the spring force is going to be pointing to the right. So we need to take care of that change in direction or change in sign in our model before we can apply it to Newton's second law. And in the scenario that we just described, where positive direction is pointed to the right, then our spring model that we could put in could simply be F sub s is equal to negative k x minus x naught. But what you'll find is that even though this is the model that's given in most textbooks, you can't just always apply a negative spring constant multiplied times the displacement. So for example, if the spring were on the other side of the mass, then that's going to change the sign. Or when we begin to work in multiple dimensions, this problem becomes more complex and we lose the intuition on the situation. So we're going to systemize our methods on how to apply a spring force to these models. There are 3 steps that we take when applying a spring model. So the first step is in the free body diagram. We want to draw an arrow from the attachment of the spring to the mass. And so the attachment would be, in this case, on the wall and then to the mass. So on our free body diagram, what we see is that we have our mass m, and then F sub s will always point in the direction toward the mass. So in the second scenario, our free body diagram would look like this. In the third scenario, our free body diagram would look like this. And the second step is always the same. We're going to write the scalar equation as F sub s is equal to a negative spring constant multiplied times the displacement. Now this takes us back to the original spring model, or the one that you see in most physics or engineering textbooks. But there's still one more step. And that's to adjust the sign based on the direction of F sub s on the free body diagram that's relative to the positive coordinate. And so applying this to our system as shown, what we have is our free body diagram where we have F sub s pointing from the attachment to the mass, and then our scalar equation for our system is equal to F sub s is negative k sub 0 multiplied times the change in displacement x minus x naught. And then we write Newton's second law, which is F equals ma, and the only force that's acting on the system is F sub s. Now here's where we make our decision about the direction, because in this system, our free body diagram shows that it's pointed to the right, which is also in line with positive x coordinate, and so we leave our sign the same, and then this is equal to m, and then our acceleration is x double dot. So we substitute in negative k, x minus x naught is equal to m x double dot, and then solving for the equation of motion, it's x double dot is equal to negative k divided by m multiplied times x minus x naught. So what we've done here is we've defined a systematic three-step process that you can always use to apply springs to dynamic systems. Now, we'll expand this when we start using our vector notation. We'll start incorporating vectors into this. So far we've only been using scalars. And what's nice about this is that you can use this process, even though here we only had a single spring and a single mass, but you can use this process for multiple springs and multiple masses using the same three steps.